This is the Chapter 9 review for geometry. You can be found on these pages, and you'll notice that I may not have assigned all the problems that I have in this video. I'm going to go through all 25 that are in the Chapter 9 review, but if that is not one that's assigned, you don't have to do that one, but you can still listen. If you wanted to, you could learn a little something new if you wanted to. So starting off here, this is from 9.1. You may or may not have problems assigned from 9.1 depending on the year you are watching this, so just make sure you check your assignment list to see what you need to do. So I'm going to color code some stuff here, and I'm going to say, first of all, I'll go with that here. I'm going to put the small triangles in red, the smallest triangles in red here, and I'll put the smallest triangle right here in red, and the smallest triangle over here in red. So I'm going to compare similar parts of these triangles to set up proportions. And if you look in the book, they've got all these fractions, and that is what we need to set up with these. But to try to memorize what fraction is supposed to go with what, I think that's more complicated than it needs to be. I think the better way to think about this is to think about these similar triangles in such a way, and I'm just color coding them to make them a little easier to decipher what's what, to figure out what's what here. So there's that. And then the green one is the big one around the outside. I'll do that in each one here, make that look a little nicer. That's looking good there. So the big green one here, and the green one here. So we're going to compare, and just for ease of comparison, got those color coded now here. So this angle right here, I know this would have to be 90. I know this would have to be 90. I know this one, I kind of covered that up here, but that's 90. This angle right here is 90 degrees. This is 90. So you have three similar triangles in each picture based on the type of picture you got here. So let's do number one, and let's set up a proportion first with that. So let's solve for x first. I notice I have x in the 6, so I could set up a proportion saying x over 6. That's this small leg of this red triangle compared to the hypotenuse of the red triangle. So I need to compare small leg to hypotenuse in another triangle. And I see the green triangle has that relationship. I have the 6 is the small leg and the 9 is the hypotenuse. So that is a valid comparison. If I cross multiply that, I have 9x equals 36. I can divide both sides by 9, and I can get x equals 4 from there. So that's what x equals. To solve for y, a similar thing here. I notice that I have a y and a 6 here. I've got a y and a 9. I could use one of those two possibilities. I notice if I look at, I could also use the fact that I have 4 now. I could plug that back in here too, but let's try to do this just with these three, just with the y, the 6, and the 9. So I noticed that I've got a y and a 9. So let's see if this works out. This might work out for us. We've got in the green triangle, that would be the longer leg and the hypotenuse. So long leg to hypotenuse. Do I have another long leg to hypotenuse comparison? So I'm not seeing that comparison right now as I look at that, but I do notice that I could actually replace this. Let's try this. So let's replace it with 4. We just calculated that. That means this one would have to be 5 because 9 minus 4 gives me 5. So let's erase what I had here. Let's see if we can determine a different way to solve this. So I have, this looks like, if I look at the blue triangle, this could possibly work out for me. This looks like maybe it's going to work out. So here's a comparison that I see. I see that 5 over y, that would be in this blue triangle, the long leg to the hypotenuse. I have to do a long leg to hypotenuse and something else. I see the green triangle has this long leg to hypotenuse like this. I can't have two variables to solve for in one equation. That doesn't let me solve for one of the variables, but I can have the same variable twice. That's okay. And so I'd have y over 9. That is long leg to hypotenuse in the blue compared to long leg and hypotenuse for the green triangle. If I cross multiply that, it gets me y squared is 36. Or not 36. I'm sorry, 45. Just thinking about the previous one. So that means I can take the square root of both sides, and that gets me the square root of 45, but square root of 45, that's the same thing as the square root of 9 times 5, breaking down the part into its perfect square constituent parts, and this I can take out. Square root of 9 is a 3. So this simplified radical form is 3 radical 5 for that one. Let's move on to number 2. So number 2, you have, looks like, I notice I'm going to try to solve for x first if I can. I've got this x, I've got this 9. This 9 looks like the short leg of the red triangle, and the x looks like the hypotenuse. So I'm going to try this comparison, see if this works. Short leg to hypotenuse. Do I have another short leg to hypotenuse that would only use x or numbers I actually have? Yeah, I have x as the short leg of this green triangle, so I'll put that on top. Compare short leg to short leg, compare hypotenuse to hypotenuse. X is the hypotenuse of the red triangle, 25 is the hypotenuse of the green triangle. And so from here, cross multiply, you get x squared is 225, and then from there you can take the square root of both sides. This one ends up being a nice whole number for us. X is 15. No units included, so I don't have to include units there either. And so if this is 9, this might be helpful for us. I'll write this in there. That could help us possibly. So this is 16 for that blue side. And so if I have that, I see something that would definitely be helpful there. I can replace now this x with a 15, and I notice if I look at the blue triangle, I have a y over 16. I could say I have short leg over long leg. Let's try that comparison, see if that gets us somewhere. These kind of, you do some trial and error. You got to plug in what you know and then try a different proportion. If the one you did doesn't work, or the fraction you tried at first doesn't work, try a different fraction and see if you can get a similar relationship in another triangle from there. So this is y over 16, and I notice this is 9 over, this was short leg to long leg. In the red triangle, this would be short leg to long leg. It would be 9 over y. So we could cross multiply that and get y squared is 16 times 9. That's not coming to me right now, so I'm going to take my calculator out. 16 times 9 is 144. I knew that. I just forgot it momentarily. Sometimes making these videos just kind of lose my train of thought for a moment. So taking the positive square root, since this is a distance, we're saying that y would have to equal 12 there. And so now we've got, in this last one, we've got 3 variables to solve for. So let's see if x is possible to solve for first. I would hope they would do that for us that way, but maybe not. Maybe we should solve for y or z first. So let's see if this is possible to solve for x first. Well, actually, I look at this and I say, hold on a second. No, take that back. This is y. If we figure out x, y will be really easy to figure out, because we just take x minus 27 would give us the y there. Let's see if I'm noticing anything else. I am noticing I could actually solve for z right now. So I'm going to start by that, because I notice I have a right triangle right here, and I could use the Pythagorean theorem. So I'm going to use that here. I may be able to use similar triangles as well, but I'm going to use the Pythagorean theorem just because that's what I saw first as a possibility. So I'm going to say that that squared plus that squared equals 36 squared. In the blue triangle, that would work out. 27 squared, 27 times itself is 729, and 36 times itself is 1296. So we have 729 here, we've got 1296 here. If you subtract 729 from both sides, that will leave you with, take this minus 729, and we get 567. So z squared is 567. And you take the square root of both sides again. Square root and square would cancel out. You'd have z is going to equal, and then you could test this if it's divisible by a perfect square. I notice the sum of the digits is 18, and a little trick for sum of the digits being 18. If 9 goes into that number, the sum of the digits, 9 actually goes into there. So I'm going to try this first. I know 9 is going to go into there, and I don't know how much off the top of my head, so I'll try that. It looks like 63. So I can say this is the same thing as that. If I wanted to go one step farther with that, I could take out another 9 from this. So I have 9 times 9 times 7. And I know 9 times 9, that's 81. If I take the square root of 81, if I split it up like that, I can think of it like that too. This is going to be just a single 9 coming out. This would be 9 radical 7. So this is one way I saw to do this. There might be another way, which we might talk about after solving for these other ones, but I can replace z now with 9 radical 7. So there may be a similar triangles way method to do this, but we'll get to that. We'll see if that's possible in a little bit. So if this is 9 radical 7, this is 27, this is 36. Let's see if we can figure out a way to solve for x or y. So I'm noticing I've got here in the blue triangle, I've got the short leg and hypotenuse. And let's see if I have a short leg and a hypotenuse somewhere else. So I've got a short leg here, but I don't see the hypotenuse for the red triangle, so it doesn't look like that will work for us. I could possibly do some other things with x here, so let's see what else we got. So again, this is kind of a trial and error type thing. We don't have the hypotenuse of the red triangle, but I do notice I could do this long leg to the short leg for the blue triangle and do the long leg to the short leg for this red triangle using the 9 radical 7 part. So this is one valid comparison. This would be long leg to short leg. I could do short leg to long leg if I wanted to as well, but you just got to keep them consistent going from here to here. So 27 over 9 radical 7, and then over here short leg would be y over 9, or I should flip-flop that, I'm sorry. Long leg over short leg would be 9 radical 7 over y. We could cross multiply this. If I go back up here, I know that 9 radical 7 times itself is actually the same thing as this. I just broke that down already. So if you worked all that out, you'd end up getting 567 on the one side is the same thing as 27y on the other side. So if you square 9 radical 7 in a calculator, that would verify that. But again, right here, this was the same thing as 9 times the square root of 7. That was the same thing as the square root of 567. So I feel like there's no reason to get out the calculator for that. But we could divide by 27 here to get our final answer. We should get y is 567 divided by 27. Y is 21 right there. And so if this is 21, I'll replace that with a 21. Now if I know this is 21 and this is 27, that makes this one really easy. Just do 21 plus 27. That means that x would equal 48. And so are there other potential ways you could have solved this? Quite potentially, yes. I just saw this as the first way that came to my mind. But if you found a different similar triangles way or Pythagorean theorem way, you could do that here. We had to use similar triangles here and here though before we could get anything. We couldn't use the Pythagorean theorem here, and we couldn't have used it over here to solve for any of those. Okay, so now moving to some problems from 9.2. Let's check these out. The variables r and s represent the lengths of the legs of a right triangle, and t represents the length of a hypotenuse. So t is my, in a sense, you've got a squared plus b squared equals c squared, and we were writing it with the c out in front, so let's do that instead here just to talk about it more clearly. So c squared, we're trying to figure out one of these missing parts. But they're saying t represents the longest side, the hypotenuse. So instead of c squared, I would say t squared equals, and then r and s are the legs. So r squared plus s squared. So we're thinking of it in terms of this instead of the c, a, and b. So let's take number 4 here. Let's find the unknown value. We're finding t is missing here. So we're going to have t squared equals r squared plus s squared, 12 squared plus 16 squared. From there, it's a matter of just working out the arithmetic. So this is 144, this is 256, this becomes 400. You take the square root of 400, and it comes out to a nice clean whole number, and that is t equals 20. And so was this a Pythagorean triple? Do you have 3 whole numbers here, here, and here? Yes, it is. So Pythagorean triple, you would say, yes, it's a, we'll just call it PT for Pythagorean triple. Okay, let's check out number 5. R is 8. T is 12. What's missing? S is missing. So we're going to have T squared is 12 squared equals R squared would be 8 squared plus whatever S is squared. This is 144 again. So 64 plus S squared. You subtract 64 from both sides. You're left with, this time, 80 equals S squared. You take the square root of both sides. This does not become a nice clean whole number, but there is a perfect square that goes into there. 4 works, but 16 is a bigger one that works, so let's use 16. This comes out as a 4, so you have your final answer. This went away, sorry, so there's no squared part left. So your final answer should be 4 radical 5. Is that a Pythagorean triple? Well, this is a whole number, this is a whole number, but this is not a whole number, so you would say no, not a Pythagorean triple. Number 6, same sort of thing going on here. We've got 34 squared is my T squared part here equals S squared is the part we have. R squared is missing, so I'm going to say R squared plus we have 16 squared. 34 squared, that one I don't have memorized, so I'll put that here. That is 1156. So we have 1156 equals R squared plus 256. You subtract 256 from both sides. That leaves you with 900 right there. So we have 900 equals R squared. You take the square root of both sides, and you have that 30 equals R. Is that a Pythagorean triple? Do you have 3 whole numbers right here, here, and here? Yes, you do. And so you have another yes. You have a PT. You have a Pythagorean triple. And then let's do number 7. I think I'll have enough room for that right here. So here we've got R is 4, S is 6, T is a missing part in this one. So you got T squared equals 4 squared plus 6 squared. What's 4 squared? 16. What's 6 squared? That's 36. So you have T squared is 52. And again, take the square root of both sides. Excuse me. You'll have T equals, this would be biggest perfect square that goes into there. The only one that goes in there is 4. And then this 4 comes out as a 2. So you have T is 2 radical 13. Is that a Pythagorean triple? You've got whole numbers here and here, but you do not have a whole number here. So this would be no, it's not a PT, not a Pythagorean triple. Let's move on now to these types. So decide if these can represent the lengths of a triangle. We've got our steps here. What we're trying to see first of all is C squared, sorry. Remember our step 1. We need to figure out, let's just go back and bring up the notes actually for this lesson to review that. And so here was the notes from 9.3. Step 1, we're supposed to check if A plus B is greater than C. We need to see that the 2 smallest sides added together actually is more than the third side. If it's not that way, we don't even have a triangle to start out. So I feel like we should check that here, so let's do that and see if it works. So that is what we need to check. We need to decide whether they can represent the side lengths of a triangle. So let's check that first. So I'm going to write it like I did before. Step 1, we will have in our notes before. We had 6 plus 7. That's your A and your B. Is that greater than C? Is it greater than 10? Yes, it is. So step 1 checks out. And then step 2, just as a reminder here how we were doing that before, so just keeping that same format. Remember to also make sure you look carefully. You might even want to label these first as your A, your B, and your C. Over here, this is my A, B, and C. They happen to be in order, but they might not be listed in order. You got to be careful. A and the B are the 2 smallest ones, and your C has to be the biggest one. And then here, for radical 5, I'll just do this work up front here. What's radical 5? Just to check this, just to make sure. Radical 5 is 2.23, and that times 4, 2.236. That times 4 is 8.94. So is 9 a little bigger than that? Yes. So this is actually my B, and that is my C. But important to make sure that that actually works. So this checked out. And now let's check step 2. So we're comparing C squared to A squared plus B squared. So let's check that out, make that comparison just like we did before. C squared compared to A squared plus B squared. So I'm going to, for this first one at least, just write it out like that as a quick reminder. That's what we're checking with each one of these, as long as step 1 works out. So this is 10 squared. What is that compared to 6 squared plus 7 squared? This is 100. And then this is 36 plus 49. 36 plus 49, that's 85. And so we have 100 being greater than 85. That means, since the C squared part is bigger, when that was bigger, remember that's when we have an obtuse triangle. So we're comparing that, and that was back here with the converse of the Pythagorean theorem. So if C squared is equal, it's right. If C squared is less, it's acute. If C squared is greater, it's obtuse. And so we have C squared being greater, this is obtuse. Number 9, you've got the same sort of idea here. Compare first, do step 1, compare A plus B, and see if it's bigger than C. So 9 plus 40, is that bigger than 41? This is 49, that's bigger than 41, so that checks out. Yes, it is. Step 2, checking C squared compared to A squared plus B squared. This time I'm just going to go right ahead and plug it in right away. So 41 squared compared to 9 squared plus 40 squared. I could write 40 squared plus 9 squared. Flip-flopping those wouldn't really make a difference, but I can't flip-flop 41 over to here. 41 squared is 1681. 9 squared, that's 81. And then 4 squared is 16, so 40 squared is 1600. And it looks like these two, or these sides, are equal. And so if they're equal, that's when we say we have a right triangle. This is actually a Pythagorean triple here. 9, 40, and 41 works in the Pythagorean theorem. All right, let's check this one out. Step 1. You got to compare A plus B. Is A plus B is 8 plus 12. Is that greater than 20? Is that true? Well, 8 plus 12 equals 20. So it's not greater than 20. And so this is not even a triangle. If it's not a triangle, please, please, please do not check and see what kind of triangle it is. It's not a triangle, so there's no reason to continue here. So number 10 is done. You can't make a triangle if these are your 3 sides. Number 11, let's check that one out using the same idea. So this 3 plus 4 radical 5, we said 4 radical 5, we did the math on that one. Let's do that again because I forgot exactly what it was. I think it was 8.9 something. 4 times square root of 5, 8.944. So this is approximately 8.94. We'll write it like that. I'll put that in red above there. So this is like saying 3 plus 8.94. Is that greater than 9? And I can just finish that thought up here. Is that greater than 9? This is going to be 11.94. So this checks out. It is greater than 9. So we can move on to step 2 and see what the comparison actually is. So step 2, we have 9 squared is what compared to, I should write, if I'm going to keep it consistent, I will keep it consistent. It doesn't really matter if I flip-flop the A and the B, but I'll put 3 squared plus 4 radical 5 squared. This is 81. And this compared to, this would be 9. You're essentially distributing this power to both parts. So you have 4 squared times radical 5 squared. And a square and square root just cancel each other out. So here you have, hello, I don't know if you heard that on there, but that was the door closing. The janitor's closing the door again. 9 plus, this is 16 times 5 here. The square root and square will cancel out here and here. And so 16 times 5, that's 80, and so we have 81 as being less than 9 plus 80 is 89. That means the c squared part, that was the smaller part, that would mean this would be acute. So we do have triangles in each case here. I guess we could say that it says decide whether it is. We could say yes it is, and this one yes it was. This one not a triangle, so we didn't need to check. And this one yes, it was in fact a triangle and it is acute. Moving on to number 12 here. So an isosceles right triangle has legs of the length 3 radical 2. Isosceles right triangle. So it's a right triangle and it's isosceles. It says the legs are both 3 radical 2. So it's going to look like that right there. Find the length of the hypotenuse. What do we know about isosceles triangles? We know that their base angles are the same. So I'm going to use the shortcut on this one. This is 45 degrees. This is 45 degrees. And we should remember 1, 1, rad 2. That's the ratios here. This is the 1, and the rad 2 part. And so we're taking this number and multiplying it by radical 2. This one times rad 2 times radical 2 here will give me whatever this value is. So 3 radical 2 times radical 2. That's like saying 3 times radical 2 squared. The radical 2, or the radical and the square cancel, so you just have 3 times 2, which equals 6 on this one. No units are given to me here, so I just leave it like that. All right, number 13. The diagonal of a square is 6 inches long. So let's draw a picture of this one. Let's draw a square. I'm just going to freehand it here. And so the diagonal of a square is 6 inches long. So that's like something like this. It's cutting that right in half like that. You know squares have these 90-degree measures in the corners. And if I'm splitting it in half like that, this is going to be 45 degrees here and 45 degrees here. I also know that this and this have to be the same because it's a square. Squares have all the same sides. The side lengths are all the same. So find its perimeter and its area. And so, I'm sorry, that's why I was like, that's a really easy problem. Why are we even doing this in this chapter? This is the perimeter is going to be based on those side lengths. This though right here, this is 6 inches long. So the hypotenuse is 6 inches long. I know that these are all the same. So again, the same ratios apply here. This is the rad 2 part, this is the 1 part, and the 1 part. But now we're going from here to here. This is where we have to divide by radical 2 instead. So this 6 divided by radical 2, we can't have a radical on the bottom, so we got to multiply by radical 2 over radical 2. And you get 6 radical 2, and then this becomes the radical 2 squared. Just to do that intermediate step, you could probably leave that out, but that would cancel out with that. You'd have 6 radical 2 over just plain old 2. This reduces to 3 and 1, so you have 3 radical 2 over 1, which is just 3 radical 2. So this is important. This is what each side length is. So you have 3 radical 2, 3 radical 2. You have that 4 different times, 3 radical 2 and 3 radical 2. So what's the perimeter? The perimeter, you're going to take 3 radical 2 and either add it 4 times, or you can think of that being the same thing as multiplying it by 4. So you have 12 times radical 2. You have that many inches for the perimeter. Perimeter is just adding up the sides, going around the shape. And then the area is going to be side squared. So a side is 3 radical 2. So you have that squared. Think of distributing the power here. This is the same thing as 3 squared times radical 2 squared. Radical and square cancel here. You have 9 times 2, which is 18. And area is in units squared. So this is 18 inches squared. And it doesn't say to round off, but if you did round this off, you would get about 17.0 inches rounded to the nearest tenth. Number 14, a 30, 60, 90 triangle. So I'll draw something like that. This would be my 30-degree measure. That's the smaller one, 60 and 90. Has a hypotenuse of length 12 inches. And what are the lengths of the legs? So I'm going to call the short one X. I'm going to call the long one Y. And remember, when we have a 30, 60, 90, our ratio is 1 to rad 3. So 1 to rad 3. That's the important part to remember. The rad 3 is about, if you forgot what that was, you take out a calculator, you can type that in. It's about 1.7. So this makes sense that this would be 1.7. 2 would be the longest part because it's the hypotenuse. So what are we going to do here to go from this to this? Well, we would need to take this and divide it by 2 to go back to the ratio, or to go back to 1. So if we're at 2, we want to go to 1, divide by 2. So that ratio will hold like that. And so we're just going to take 12 divided by 2 will get us what X is. So 6 equals X. From there, it becomes an easy matter of just taking that value and multiplying it here to get the Y, multiply it by radical 3. And so once you know this one, piece of cake, upside down, inside out, backwards, etc. We have, this was 6, and so we have 6 times radical 3, which is the same thing as saying 6 radical 3 without the multiplication in between there. And this is in inches, so I should put inches right there, and I should put inches right here. That equals my Y value. So the longer leg, 6 radical 3, and the shorter leg is 6. If you plugged 6 radical 3 into a calculator, you would get about 10.4 inches. We'll just do that quick here. So 6 times 3, taking the square root of that, multiplying it together, 10.4 rounded off to the nearest tenth. It just kind of depends what they ask for. So if you were asked to round, you'd have 10.4 inches right there. Let's move on to number 15. Equilateral triangle now has sides of length 18. So draw your best equilateral triangle. You've got to draw the pictures with these, otherwise it's really hard to visualize what's going on. So that would be true. I'm drawing in that in there because I realize that I need to find the altitude. This is going to be the altitude of the triangle. It says the side lengths are 18, so I know that all three of these would be 18. I could put 18 inches down here, I could put 18 inches here, I could put 18 inches here. That would mean this would have to be 9 right here, 9 inches, and 9 inches right there and right there. And so from there, find the length of the altitude. So I'm going to call the altitude, I'm just going to go with X. So I'm trying to find the length of X. I know based on equilateral triangles that this is a 60-degree measure. This one's 90. I already got that in there. And that one would have to be 30. It cuts that angle in half. So you have a 30, 60, 90 triangle. Your ratios then are going to be, you have your 1, 2, rad 3. So the short leg is the 1 part. You have the the hypotenuse is the 2 part, and you have the long leg is the rad 3 part. So what are we given here? We're given that this is 9 inches. So this is a pretty easy one to get because we just need to take this and multiply it by the rad 3 part to get what X is. So your X is going to equal, you had 9 inches times radical 3. So you have 9 radical 3 inches for the altitude. If you were to plug that into a calculator, this is, did I say inches? I meant to say centimeters. Sorry about that. I meant to be doing that all along here. So this says centimeters, not inches. I was still stuck on inches from before. I think we had that before, right? Yeah, inches are right there. So we have centimeters instead. And if I were to put that into a calculator, let's just do that quick. We have 9 times square root of 3 is about 15.588. So around that, it would be about 15.6 centimeters. And so you have that. You want to figure out the area of the triangle. Area, remember, of any triangle is 1/2 base times height. And your base is this part right here. It's the 18 part. Why don't I highlight that in red just to make that stand out a little better. So here's your base right here, and here's your height or your altitude right here. So we're taking those values and plugging them in. Your height, better to use the exact answer until the very end, as long as you can do that. This would be 9 times 9 radical 3, which would be 81 radical 3 centimeters squared. It's an area. You plug that in to get an approximate value, you would get about 140.3 centimeters squared if you round that to the nearest tenth. Let's take a look then at number 16, 17, and 18. So we should remember with these ones now, SOHCAHTOA. So SOHCAHTOA, or if you remember Oscar had a headache over algebra, and just remember that it goes sine, cosine, tangent. Either one of those ways will work. Whatever you like better is a good way. If you come up with your own way and you like that better, use that too. Just whatever helps you remember best. So SOHCAHTOA. Here we're supposed to find the sine, cosine, and tangent of the acute angles. So the acute angles in this one would be L and J. K is the right angle. We're finding the sine, cosine, and tangent of L and J. Why don't I start with J, because that comes first in the alphabet, just to do it that way there. So we have the sine of J. Sine is opposite over hypotenuse. So we have the opposite of J is 11. Hypotenuse across from the right angle is 61. So 11 over 61. The cosine of J would be adjacent over hypotenuse, 60 over 61. And then the tangent of J is, tangent is opposite over adjacent. The TOA part, it's 11 over 61. And do the same sort of reasoning rationale for the sine of L, cosine of L, and tangent of L. And it looks like we will need to round these off to 4 places too. So we'll get to that after we get all the fractions. So the L here is going to be taking this, and we're doing sine first. So we've got opposite over hypotenuse, that's 60 over 61 for that. Cosine of L, 11 over 61. Tangent of L is 60 over 11. If you plug these all into a calculator and you go to 4 decimal places like it asks you to, read the directions. Always read the directions. Some of you have gotten in trouble in the past for not reading the directions and doing what it says. You have the sine of J would be 0.1803. This comes out to 0.9836. And then this comes out to 0.1833. Sine of L is 0.9836. 60 over 61, the same thing here. So we had before. Oops. 11 over 61, that's the same thing as it was up there. And then the tangent, the same thing as it was, or not the same thing, sorry. I got a different number here. I've got 5.4545. So that's all that. This, I guess I'll box that in. The whole thing is my final answer. I got to have all 6 pieces there. So doing the same thing here for the sine of acute angles, and this one are P and N. So I'll do N first. And I'll do P from there. And you'll notice each one of these, it's just a fraction answer. If you're saying the sine of a certain angle, it's always just a fraction, what it equals here. So sine of N, cosine of N, tangent of N, opposite over hypotenuse, 12 over 37. Adjacent over hypotenuse, 35 over 37. Tangent, opposite over adjacent, 12 over 35. If you do that for P, sine of P, here's P, you go opposite over hypotenuse, 35 over 37. Cosine is adjacent, 12 over hypotenuse, 37. And tangent of P is going to be opposite over adjacent, 35 over 12. Plug these into a calculator to get your approximate values. Rounded to 4 decimal places will look like this. So we have sine of n, this is 0.3243. Cosine of n, 35 over 37, is 0.9459. And then 12 over 35, 0.3429. And then these ones got the same thing here as before, so it's right there. This one's the same as this one, so that's 0.3243. And then tangent 35 over 12, it's a little less than 3, it's 2.9167. So that's our whole answer for that one. And then finally number 18. I feel like we got this down pretty well, but we're going to finish up with one more. This one throws a little twist into there, so good to see that here. Our acute angles, in this case, A and B. So we have sine of A, cosine of A, tangent of A, and sine of B, cosine of B, and tangent of B. So it says to express each value as a decimal rounded to 4 decimal places. So this would be our final answer. All these values right here, all these values right here, and then whatever we get over here after we work this all out. So sine, cosine, tangent for each one. The sine of A, you got opposite over hypotenuse, 7 over 9. Cosine is going to be, you'll have this 4 radical 2 on the top over 9. And then tangent of A is going to be opposite over adjacent. So you'll have this. You'll have this radical on the bottom. But since we can round our answer to 4 decimal places, we don't need to get this in simplified radical form. We can just go right to a calculator and figure it out from there. The sine of B, you've got 4 radical 2 over 9, the same as the cosine of A. The cosine of B is the same as the sine of A, 7 over 9. And then the tangent of B is the tangent of A flip-flop. So 4 radical 2 over 7. You put these all into a calculator, 7 over 9, that's 0.7 repeating or rounded to 3 decimal places. You have that, 0.778. Bracket that off here. This, we'll show you this one in the calculator just so you know how to do this. You have 4 times radical 2 equals this much, and so take this and divide it by 9. Your answer should be 0.6285 rounded to the nearest 4 decimals. And then this plugged into a calculator, do the same sort of thing. You'll want to do this first. Think of this kind of as being in parentheses. It's always like invisible parentheses are there when you have fractions. And so it's 7 divided by 4 radical 2. This would be 1.2374. If you plug that into a calculator, plug the rest of these into a calculator, you're going to get the 0.6285. And I just noticed an error I made up there. I did mean to go one more with that, so this should have been 4 decimal places. That's 1, 2, 3, 4. There we go. And so this one now is 1, 2, 3, 4 decimal places there. And then 4 radical 2 over 7, that is 0.8081. So our final answers here would be what you see right there. Let's move on to number 19 now. So solve the right triangle. We're supposed to find all 6 parts. So let's do the easy ones first, the ones that are actually there. The measure of y is 90 degrees. I can see that xz is 12. And I can see that xy is 8. So I got 3 out of the 6 parts given to me right there. And so now let's find the missing parts. When you have one like this, you're going to have to solve for x first using the Pythagorean theorem. So I've got x squared plus 8 squared. Leg squared plus leg squared equals hypotenuse squared. That means x squared plus 64 is 144. Subtract 64 from both sides. You're going to be left with x squared equals 80. Take the square root. I think I remember doing this one earlier in this review, but if we don't remember, this will cancel out here and here. This is the same thing as 4 times 20, but that's the same thing also as 16 times 5. That's the bigger perfect square that goes into there. Take that out. You have 4 radical 5. No units given, so that is that is what that is. And you could say this equals zy or yz as well if you wanted to. So that's part 4 of 6 parts that we need. So to figure out those other ones, we've got now, we need to figure that out. I want to use the values that are already given to me here. So I want to use these two, the 8 and the 12, and I want to compare it first to the x. So looking at x, 8 and 12, what ratio would I use for that? I see I have adjacent and hypotenuse. The co part of SOHCAHTOA is cosine of x is adjacent over hypotenuse x, or 8 over 12. I could simplify that fraction first before I do anything else. I could make that 2 over 3. And then from there, this is where we do that cosine inverse thing. So cosine inverse, cosine inverse, cosine and cosine inverse cancel with each other. And you have x is equal to the inverse cosine or cosine inverse of 2/3. Take your calculator out at that point. Type in 2/3, that's 0.6 repeating. And you're going to take the inverse cosine of that value and get 48.18. And so I'm rounding the decimals to the nearest tenth. It says we have that this is now the measure of x. I'm not just saying x itself because x is right there, but the measure of angle x is approximately 48.2. From that point, if you were quote-unquote lazy, you could say, okay, the other one's going to be 90 minus this. If you're sure you did this right, then you wouldn't have to do that. You could also say that if we took, erase this here, you could look at this value, your 8 and your 12. I would use those values rather than the radical value. Easier to deal with those whole numbers. You'd have opposite over hypotenuse, so you could set it up like this as well. So just to get that extra practice with seeing one like this, I'm not going to do just 90 minus this. I'm going to see what it actually comes out to just to get the extra practice. So sine of y is equal to opposite over hypotenuse. So from there, now it's a matter to get rid of the sine. You get just y by itself. Take the inverse sine of both sides. Take the inverse sine here. That will cancel out there and there. You're just left with plain old y, but we want to put the measure of the angle because that's what we're referring to. What is that measure of the angle? This you can reduce to 2/3 again. And so now we put in 2/3 into a calculator, take the inverse sine of that. Once again, we'll clear this out. We've got 2 divided by 3, and taking the inverse sine of that, we get 41.8 rounded to the nearest tenth. And that should make sense because this one plus this one is 90, and the 90 plus the extra 90 gets you the 180 in the triangle that you expected to get. Right, now solving the right triangle for this one, that looks like, let's make that a little clearer, that's an F, that's a D, and this is 50. So this one's pretty easy to figure out. The measure of F is going to equal, you'll have 180 minus these two, or you could think of it, since one of these is a right angle, you can just think of it as 90 minus 50, which is 40 degrees. So this is one of the pieces. You've got 3 of the pieces given to you, 90 for measure of angle E. You've got the measure of angle D is 50, and you're told that DF equals 20. So here's 4 out of the 6 parts already. And then we just need to solve for this. So I can use, I'm going to look at this, I'm going to look at this one, and this one. I'll start with D. This is opposite of that acute angle here. So we have opposite, and then this one is the hypotenuse across from the right angle. So you have opposite and hypotenuse. That's the SO part. That's the sine part of SOHCAHTOA. So you have sine of 50 degrees is opposite D over hypotenuse 20. So we can solve this for D. We can think of that as a fraction and cross multiply. And we're just going to get D by itself on one side equals 20 times the sine of 50. From there, calculator comes out, take the sine of 50, multiply it by 20, and we get about 15.3. So approximately 15.3. No units given, so I'll leave those out. At that point, you could use Pythagorean theorem with this rounded answer, but the better way I think to get the answer would be to go back to what was given to you to start and see where we can go from there. So I see that I've got, I see that I've got this 50 degrees again, and I think the 20 and the F would be the best way to go about doing that. So we have now the cosine, we have F is adjacent to 50 degrees, so adjacent over hypotenuse. Helps get a fraction, helps you see what to do, cross multiply. You've got F equals 20 times the sine, or the cosine of 50, sorry. And so if you plug this into a calculator, let's see what we got there. We have 50, cosine of that times 20 equals about 12.855. And so we repeat that, or that 5 here will round off to, or round the 8 up to a 9. So we have 12.9 right there. So the 3 missing parts were here, here, and here. These were the 3 given parts. And we got one more solving the right triangle before we move on to the 9.7 lesson, which you may or may not have had to do depending on on the year that you're looking at this. But that's an 8 right there, in case that's not clear. It should be clear in your book. This is an S, and this is 15 right here. So we're trying to solve for this part, this S part first, it looks like. So I'm going to write down what I know based on the picture. Just looking at that, you have that measure of angle S is 90 degrees. You've got the fact that ST equals 8, and you have the fact that RS equals 15. You can start with that as 3 out of the 6 things. And then to solve for S, this is a matter of using Pythagorean theorem once again. So we have 8 squared plus 15 squared, leg squared plus leg squared equals hypotenuse squared. This is 64. This is 225. This is still S squared. This would be 289. You take the square root of 289. And what do you know? They gave us a nice Pythagorean triple here. This is 17 for S. No units, so we can leave it like that. From there, we can figure out what these angles are based on sine, cosine, and tangent. So I'm going to use this, this, and this first. So I'm going to solve for R. I would have that this is opposite and this is adjacent. This is not using the hypotenuse. I'm going to use what was given to me first. That's always the best idea. In case you made a mistake here, then you're still not going to mess this up if you do this right. So we've got the tangent of R is equal to adjacent or opposite over adjacent. From there, it's a matter of taking inverse tangent to get rid of tangent. You got to do that to both sides though. And you're left with R, meaning the measure of angle R equals the inverse tangent of 8 over 15. Plug that into a calculator to see what you get. So let's take 8, divide it by 15, and we have the inverse tangent of that. It's 28.5 point, and I clicked off of that too quick. I think it was 28.1 rounded off. Yep, 28.1 degrees approximately rounded off. And then from there we can figure out as well, using those same two, I'm going to keep it with using those two because those were given to me originally. Again, if I made a mistake here and I used that value later, it would mess up everything else too. But if I use what's given, that's not going to mess things up. If I did make a mistake here, that would just be a localized mistake, you could say. So the tangent of t would just be here opposite over adjacent, so we just flip-flop the fraction from before, 15 over 8. And now we've got inverse tangent both sides here. You have the measure of angle t now is the inverse tangent of 15 over 8. Plug that into a calculator. Let's see what you get. 15 over 8 is that, and take the inverse tangent of that value. And oops, I went one step too far. Let's put that back in there. I didn't mean to take the inverse tangent twice. We have the measure. I did something else wrong there. What did I do wrong there? 15 divided by 8. Did not clear that completely. 15 divided by 8. Now let's take the inverse tangent again. There we go. So 61.9 degrees. And that should make sense because if you add this one and this one, they add up to 90. And so that should make sense in terms of the picture because that one and that one better add up to 90. If this is going to be a right triangle, they have to add up to 180. Okay, so again, depending on whether or not we covered this lesson, whether or not it's a sign, you may or not have to do this. So draw a vector, PQ in a coordinate plane, write the component form of the vector, and find its magnitude. We're rounding decimals to the nearest tenth. And like magic, a wonderful graph appears. I will use colors to color coordinate these ones. I'm going to draw them all on the same graph. But let's use red for this one. So P is at 2, 3. Here's 2, here's 3. And Q is at 1, negative 1. So here's that. And if we're drawing the vector, we're connecting P to Q down here with a straight segment, a straight line segment. And so we're going to have, let's use that like that, and it's a vector, so we should put a little arrow like that there. And we're trying to find the component form of the vector and find its magnitude. So the component form of the vector, we're just saying how far, what's the change in the x values from P to Q, and what's the change in the y value from P to Q. We're going to the left 1, that's a negative 1, and we're going down 4, that's a negative 4. So for 22, the component form of the vector would look like this. You'd have negative 1 for your x component part, and you'd have a negative 4 for your y component part. And then we're trying to also figure out what that is. Let's make that real small. I don't want to make it 0, but we're trying to figure out what this is right here. We can make a right triangle like that. Why don't I do that in a lighter color than that even? Oops, I didn't want to erase that. I'll use the yellow. Yeah, I like that a little better. So this right here, what is that? This is a 1, and then this is a 4 right there. So you're doing 1 squared plus 4 squared equals, let's put this in orange. It's a little easier to see orange, I think, than the yellow there. There we go. So red, that's still the vector right there, that part. That would equal your PQ squared part. So I'm going to leave that as PQ squared. And this becomes 1. This is 16. You've got this equals PQ squared. That's 17 equals PQ squared. Take the square root of both sides. Square root, square cancel. You're left with, so to round your decimals to the nearest tenth. Plug that into a calculator. You're going to get that PQ is about 4.1. So this is the first part of your answer, that's the second part of your answer. Let's do 23. Let's use green for that one. So still using the same graph. Negative 6, 3, that's 1, 2, 3, 4, 5, 6, and then up 3, 1, 2, 3. And 6, negative 2, so you're going this direction, 1, 2, 3, 4, 5, 6, and you're going down 2 right there. So just keeping it on the same plane, this would be my green P and my green Q. And that would be my vector, the green PQ. Let's see, does this show up? That shows up pretty nice over there like that. So 23, what's the magnitude of this? What's that component form of that? How far to the right are you going from P to Q? What's the X change? So you're going 6 from here to here, and then 6 more from here to here. That's a X value to the component of 12. You're going from this point right here down 3 and then down 2 more. You have a Y component value of the negative 5 right there. So this is our component form. I shouldn't say of the magnitude, it's the component form of the vector. And then to find the magnitude, if you've seen Despicable Me, you know Vector, he says that he's that's what he says. He says, my name's Vector because I commit crimes with both direction and magnitude. Oh yeah! And he just keeps saying, oh yeah, over and over again, and it's hilarious. I love that movie. But anyways, we're going here. Let's put this in orange. This part, this value is 5, and this value is 12 right here. So we may recognize that as a pretty popular Pythagorean triple, but if not, we would work it out. Or if it said to show your work, then we'd work it out. You have 12 squared. This is PQ squared. I'll put the parentheses there just so you don't think it's P by itself and just the Q part squared. So we have 25 plus 144 is PQ squared. That's 169 is PQ squared. And you can take the square root both sides here. That'll cancel there and there. You're left with PQ, the green PQ for number 23 would be 13. And then finally I'll do this one in blue, 24. I would have a point at 2, negative 2, 0 right there is my P, and then 1, 2 is going to be right here. So that's my Q for this one. Let's draw in the vector itself. Vector right there, and right there would be that blue PQ vector. So let's circle that over here too. So I'm doing 24 in blue. So what's the magnitude of this? From P to Q, that's a change in X of 1, 2, 3. And that's a change in Y of just 1, 2. So there's your component form of the vector. And then to figure out the magnitude, consider the right triangle that's formed by it. You have a change of 2 here, a change of 3 here. And so you're taking this and doing 2 squared plus 3 squared equals PQ squared. And this would be 13 after you simplify that. Take the square root of both sides. That leaves you with your component form is just the square root. I didn't say a component form. The component form is right here. The magnitude is the square root of 13 for PQ. This would cancel out with that. And it does say to round your answers to the nearest tenth. So I would want to make sure that I do that here. PQ is approximately 3.6. Right, so one more here, 25. Let's vector U be this, vector V is going to be this, and then we're trying to find vector u plus vector v. Find the magnitude of the sum vector and its direction relative to east. And so here I've drawn in what I need. I just need the quadrant 1 for this because I just have positive vectors here and I'm adding the vectors together. There's no subtraction of vectors here, so I can say that is the case. So why don't I do this in red? I'll draw, or in blue, I guess. Okay. In blue, I'll do vector v in red. And so in blue, I will draw this vector. We are starting at the origin, like we always should if we're doing a problem like this. And let's see if I got blue ready. There we go. So 1, 2 is the component form of the vector. So we're going starting here, going from here, going to the right 1, and we're going up 2. So that's where we'll end up for vector u. So I'm going to put next to that, this is going to be a little u with the vector symbol above it. And just remember that the vector symbol, it's kind of like half an arrow there. I don't complete the arrow, it looks like that. And so from there, going 13 and 7. So 13 in the x direction, 7 in the y direction from that point right here. So 13, better count carefully. This would be 1. Why don't I make a little mark here as I do this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 is out there. Let me just double check that. 2, 4, 6, 8, 10, 12, 13. Okay, and so from there we got to go up 7. So 1, 2, 3, 4, 5, 6, 7. We've got a point right there. That's where we're going to end up. So we're ready to go here, starting where we left off with u, and we're going to that point right here. So this is vector v. That's that vector. And so what is a, or u plus v? I'll do that in green. U plus v is these two, in a sense, added together. You end up here, so if you started here and you end up here, that's what u plus v is. And so I'm going from the origin to that point right there. So it's kind of long and skinny compared to the triangle that it forms, in a sense. But that would be what that vector is. So find the magnitude of the sum vector. This green one is the sum vector. It looks like this. You got u plus v. Vector u plus vector v. That's the sum vector. Sum just meaning adding the two vectors. And so we're taking that and find its direction relative to east. And so find the magnitude of the sum vector. We've got to take this. This was at 0, 0. We went 1 this way, and then we went 13 more. So that is going to be 14. This point right here, out here, is 14. And how far up did we go? We went 2 up, and then we went 7 more up. Right here and right here. 2 plus 7 would be the 9. So the magnitude form of this would look like that. So the magnitude of the sum. Correction on my wording there. This is the vector right there is 14. Now, the magnitude of some magnitude is how long it actually is. So what is that? How are we going to figure that out? I'll bust out my orange again to think about that. So if you make a right triangle here, we can consider that right triangle. Here's my right angle. Not my best looking right triangle. Why don't I actually, since it's a little longer line there, I'll use the straight line tool to make those look a little nicer in orange. Okay, so this goes out to there, and this coming down to there. Got right angle right here. This value is 9, this value is 14. And so what does that make that equal to? You can use the distance formula too if you like that better, but I prefer to think of things using the Pythagorean theorem. I think it's just easier to think about than trying to memorize that distance formula but either way would be working just fine. I'm going to use the Pythagorean theorem though instead, so we're taking here the magnitude of this would be, we're saying u plus v, this vector is going to equal, you got 9 squared plus 14 squared. You're taking the square root of both sides to get that, and so this is equal to, if I call this the vector u plus v, how long that actually is. Sorry, I meant to, before I did that, I meant to do this too, so that u plus v, I wanted to say what it actually equaled to start. So this equals basically this right there, but in this component form. So 14, 9. This is true. So now I can take this and work this out from here. Let's call this value, I'll just call it x for right now, just to make it easier to plug in here. So you got 81 plus, this will be 196 is x squared. We add those two things together, and we're going to get 277 being equal to x squared. Take the square root of both sides, and it says, say to round decimals, yes, so we're rounding decimals to the nearest tenth. That doesn't actually say that for this one, but we will. So we'll round this to the nearest tenth. This is about, or approximately, take out our calculator here and take the square root of 277, about 16.4 is what I got there. Correction on that. This is 16.64, that I meant to say 16.6 there. Not bad on that one. So this is 16.6 approximately. This is the magnitude, so this equals magnitude. In other words, how long that vector actually is, u plus v. And again, you could use the distance formula, and now to figure out how many degrees it is, it's going to be here north of east, how much it is relative to east. And so north is going up this way, east is going this way. If I put coordinates here, this would be north, east, south, and west. When I was younger, I was told to never eat soggy waffles. That's how I remembered how this went. So north, east, south, and west. And you have the fact that this is basically what we're looking for. We're looking for what this degree measure is. And so why don't I call this y degrees, just for the sake of simplicity in solving for it. So y degrees here, this is going to be set up like this. So we have this value, we've got the opposite value right there, and we've got the adjacent value right there. So we would have the one using opposite and adjacent would be tangent. Tangent of y degrees equals opposite is 9 and adjacent is 14. So we're going to solve this for just plain old y degrees. So I would take inverse tangent of both sides here. That would cancel out here and here. And this time, since I'm saying it's degrees, I don't put the measure of y degrees. It's just y degrees equals the inverse tangent of 9 over 14. And so let's plug that into a calculator and see what we get. 9 divided by 14 is this. Take the inverse tangent of that, and you have about 32.7 degrees. And this is degrees north. So here's north, you're going kind of up in a sense, 32.7 degrees north of east. So the best way to write that would be like this: 30 degrees, 2 degrees, n of e standing for north of east. So hopefully you found that extremely helpful in your preparation for the test. Remember, we didn't cover necessarily all of the problems in this review, or you didn't have to do all the problems in this review necessarily. Just reviewing the ones you needed to. Go back, pause, rewind, reflect, rewatch, and ask questions about things if you didn't understand before you take the test coming up on Chapter 9 here. So again, let me know if you had any questions in class, and thanks for watching.